Hi there. Today I'm going to talk a bit about stress transformations. What is a stress transformation, right? What it is kind of what's laid out a bit on the stress block that we've got here. Okay, we've got a stress block. It's got stresses in the x and y directions. We found them in some convenient coordinate system, usually something that's easy to do the analysis in, right? But what we really want to know is what's happening along that purple dashed line at an angle theta from the vertical, right? Because maybe that's where a crack lives, or maybe that's where a weld is, or maybe that's where, it's a wood piece and there's some kind of grain in there, right? So we want to know what's happening along that direction. So what we have to do is either make a cut at that angle, do all this analysis over again, and do it every time we want to find a new angle, not convenient, or we find a way by which we can relate the stresses on the new angle to the stresses where we started, okay? And this is essentially coordinate systems just being names, okay? They're not like x and y is not special. X is not, it shall be the long axis of the member at all times. It's whatever's convenient at that time, okay? So just start thinking of coordinate systems as just points of view. That's all they are. We're looking at this XY coordinate system as a point of view. So really what we're going to wind up with is a coordinate system angled like this. Okay, notice how I've got this one axis, this axis that's going up and to the left, calling that T. That is going to be at an angle theta. I'll draw a little longer to highlight that as my original y-axis. And here's theta. Perpendicular to T, I'm going to have a direction N. And that, of course, is going to be at an angle theta then from the x-axis. Okay, so all I've done is taken my xy coordinate system, I've spun it up a little bit, right? I've just spun it up by, by an angle theta. Theta, we're going to say is positive if counterclockwise. And I'll say positive counterclockwise. What we're going to be interested in is the new normal stress, sigma n, the new normal stress, sigma t, and the shear stress, tau nt, that we get. And what this is eventually going to lead us to, right, longer term, is how to find the biggest possible stress using this initial setup of sigma x, sigma y, and tau xy. Because it turns out there is an absolute maximum depending on our point of view. And there is, an absolute minimum depending on our point of view. And what we want to do then is we're going to be able to use this result today to figure that out at a later time. Okay, so that's something else to keep in mind. That's the place we're going. This video, because of length, is going to focus on the axial stresses. I'll have another one with the shear stresses afterward. Okay, so what we can do to figure out sigma n at least, right? We'll get sigma t in a relatively clever way. There's two ways to do that, and one I like and one I don't, right? And when we get to that, you'll understand what I mean, right? So what I'll do is I'll start off with a free body diagram. I've just cut off that triangle, right? That triangle I've got in the corner there. I've now cut it off. I'm calling the long length here dA. And because it's a triangle, right, we can assume, first of all, the depth into the page is the same on all three sides. Okay, that's not a big deal, right? That's going to be the same. So the change in dA is going to depend on the change in the lengths of the sides of the triangle. And we can agree they're not the same length because, well, I've got this angle theta from the vertical, and this is cut out of my original box. So that's going to be perpendicular because I had a square to start with, right? So that corner is still the corner from the square. And unless that angle theta happens to be 45 degrees, and we're probably not that lucky, right? But unless it happens to be 45 degrees, the vertical and horizontal sides can't be the same length, right? So that means we need to have relationships for how dA and dA1 that I've called on the left face and dA2 on the right face are put together. And it's just trigonometry, right? My theta here, my adjacent side is dA1, my opposite side is dA. So it sounds like the dA1 should equal the hypotenuse, dA, times cosine of the angle theta. And I can say the same thing about dA2. dA2 should be equal to dA times the sine of theta. And now I can just sum forces. Now keep in mind, I'm going to sum forces here. That's why I've got these dAs floating around in the first place, right? I can't sum stresses. but I know how to sum forces. I know how to use a free body diagram and sum forces, right? So what I've done is I've multiplied each of these stresses by that little area that they act on. I can get away with this because the area is really small. It's a stress block. It's representing the state of stress at a point. So in theory, I can make that stress block all the way down to a point in size. At that point, all those approximations work out just fine. So yes, this is approximately true, but we're taking stress times area, where area is this little differential chunk, and we're using that to get force. I have 4 different axes to work with. We've got X, Y, and T. Oh boy, which ones do I use? Well, I keep in mind what my goal is in a situation like this. My goal is to have equations for sigma n and for tau nt eventually, in another video, where they're related to sigma x, sigma y, tau xy. So if I can come up with equations that isolate those without having to have sigma n and tau nt in both equations, I'm going to use those. And notice how sigma n is exclusively in the n direction and tau nt is exclusively in the t direction. So we can say, if I sum forces in the n direction and set it equal to 0, okay, I'm not going to have anything to do with tau nt. It's all going to be sigma n and the stuff I presumably already knew, sigma x, sigma y, tau xy. Okay, so when I do this, I can say that sigma n times dA, and that's going to be positive, of course, the way I've drawn the axis system. You see my coordinates there, right? The sigma x is going to have a negative component in the n direction, minus sigma x dA1, and I'll just call that dA cosine theta. That's just dA1. And now I've got to figure out how that relates, because x and n aren't totally lined up, but since x rotated into n, I can say, right, that's going to be, again, a cosine of theta. Okay. I'm going to have a contribution from sigma y, and it looks like sigma y is, again, opposite the n direction, so I'll have minus sigma y times dA2, which was dA sine theta, and that's going to be sine of theta. And the reason I know that is if the horizontal force, sigma x dA1, was needed a cosine, well, the vertical force, sigma y dA2, is going to need a sine. Right? Just the way these things work out if you've done a decent amount of statics. And I'm going to have 2 contributions from tau xy. One's vertical, one's horizontal, so one's going to have a sine and one's going to have a cosine. We already have that in our heads. Minus tau xy, and I'll just throw parentheses around the whole thing. And I've got dA1, so I've got dA cosine theta. We said because n started off life as a horizontal axis with theta equal to 0, the vertical force is going to get the sine theta. And it'll be plus inside the parentheses because it's a minus overall, and I've got the minus leading off the whole thing outside leading off the tau xy. So I've got the area, which was dA sine theta times cosine theta, and that whole thing has to equal 0. Right? I'm going to make that theta just a little bit better. It looked like cosine is 0, which I didn't want. I definitely want cosine of theta. Okay. Now, we've never talked about the area of a stress block, because hopefully we never really use the area of a stress block except as a stepping stone to get to what we need, right? Here we're hoping to use it as just forces, right, as a way to get to forces. And if we've done this correctly, it won't matter, because it shouldn't matter, the result, I should say, shouldn't matter based on how big or small I chose my stress block to be. It's an arbitrary thing, so I hope it disappears. Well, notice how every term on the left-hand side here has a dA. I can take out the purple pen, as I usually do, and knock out all those dAs. Whew. Nice. Second thing to keep in mind is we're going to need a little bit of light trig here. Okay, we'll get to the trig in a second. But hopefully you're looking at this and saying, you know, there's a trick here somewhere. It's because there is. I'm going to take everything but sigma n and put it on the right. So sigma n is equal to sigma x. And I've got cosine theta times cosine theta. Well, that looks like cosine squared theta. And then I've got plus sigma y sine squared theta. and I've got tau xy, and it looks like I've got 2 sine theta cosine theta in there. Okay, so that's what sigma n is going to be. And I technically have an equation for sigma n, but not one that lets me introduce any instinct to this whatsoever. I'd rather have a more natural instinctive equation. Here's where some light trigonometry comes in. Okay, what we can prove, if you remember some trig identities, really what it takes of all things is sine squared plus cosine squared equals 1, which everyone seems to remember if you're going to remember any trig identity. And if you remember the sums of the cosines and sines of 2 angles, what we can say with some trig identities, what we can say is that we have cosine squared theta is equal to 1/2. I'm going to make that square look a little better. It didn't come out the way I liked it to. But cosine squared theta is 1/2 of 1 plus cosine 2 theta. Sine squared theta is 1/2 of 1 minus cosine 2 theta. And 2 sine theta cosine theta is equal to sine 2 theta. And now we can start substituting these things into the equation that I have above, right? I'll get rid of cosine squared, and instead I'll have cosines and sines of the double angle, I should say. Okay? So what that means then is sigma n is equal to sigma x over 2, 1 plus cosine 2 theta plus sigma y over 2, 1 minus cosine 2 theta plus tau xy sine of 2 theta. And now I can just group this around a little bit differently. And what I'll get is sigma n is equal to sigma x plus sigma y over 2, because I've got a 1 in both of those equations on sigma x and sigma y. Each one also has a cosine of 2 theta. Just one of them is a plus and one of them is a minus. So why not call this plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta, and that's sigma n as a function of x, sigma y, tau xy, and theta. Works out pretty nicely. It's not a bad equation, really. So that's sigma n. That's the axial stress in the n direction. What about the axial stress in the t direction? Now I can do 2 things, right? I kind of mentioned that earlier. I can make another cut at 90 degrees to the angle, the cut I already have, right? I have the cut here. I can cut perpendicular to that. That'll expose sigma t. I can solve the same thing by summing forces in the t direction. Or, right? We can be clever. If we remember that n and t are 90 degrees apart, right? They're a perpendicular axis system. One is along the direction of the cut. In this case, it'd probably be this one, my index finger. My thumb is perpendicular to it. They're 90 degrees apart. So if it takes an angle theta to rotate the x-axis into the n-axis, then I got to go another 90 degrees to get the t, don't I? Right? So if we remember that, plus the cosine of an angle plus 180 degrees is equal to negative cosine of the angle. I'm using phi here. Sine of phi plus 180 degrees, well, that's equal to negative sine of phi. Well, all I have to do, because again, 2 theta plus 90 degrees, right? I'll make a note over here. 2 times theta plus 90 degrees is going to equal 2 theta plus 180 degrees, right? Because that's going to be our angle of rotation, is going to be theta plus 90 degrees. So if I double it, I get 2 theta plus 180. Sigma t is going to be the same equation as sigma n, except with a minus sign in front of the cosine 2 theta term and a minus sign in front of the sine 2 theta term. And that's it. That's all I have to do. This is the easy way to get there. And I'll go down to another page. Sigma t is equal to sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 quantity cosine 2 theta minus tau xy sine 2 theta. That's it, right? It makes sense that, for example, if sigma x is contributing to sigma n, maybe it won't contribute to sigma t because of the way the angle is set up, right? So that's kind of the consequence that we get. And instead of dealing with thetas, right, all this stuff, instead of having thetas in it, has 2 thetas now, okay? Last hit here, right, before I cut this one off and we go on to another one for the shear, right? Just a big note. Sigma n plus sigma t is equal to, right, actually let me move that down a line so I have a little more room, right? Let's think about what the sum of the axial stresses is equal to. Sigma n plus sigma t. Well, each of them leads off with a sigma x plus sigma y over 2 term. So it's 2 sigma x plus sigma y over 2. And it looks like things are going to start getting a little bit funky, except, well, sigma t has a minus sigma x minus sigma y over 2 cosine 2 theta. And sigma n has a plus sigma x minus sigma y over 2 cosine 2 theta. So that's 0. They cancel each other out. I've got a minus tau xy sine 2 theta. I've got a plus tau xy sine 2 theta. They cancel out. Plus 0. Sigma n plus sigma t has to be equal to sigma x plus sigma y. Okay? That is a given. That is something you can use if you're doing something like this. You can turn around and say, okay, did I get it right? Here's your quick dummy check, as they're called, right? You can say, okay, do my axial stresses still add up to what they were originally? If they don't, I've done something wrong. I've got to go back and try again. If they do, I'm not provably wrong. I'm not necessarily 100% right either, but at least I can prove that I'm not terribly wrong. Okay, thanks for watching. We'll have another one on shear pretty soon.